All right. Wow, a lot of people missing. Let's see. Any questions? We started talking about allocating dynamic memory yesterday and using pointers, and we're gonna dig further into that today and tomorrow. All right. Well, let's just hop into it. So our basic setup, we're going to be working with these nodes, which look almost like PA1 nodes. So we have a data piece, which will continue to be an integer, but our field that we call next is a pointer to a struct node. Whoa. Yeah, I just saw.
Your picture's upside down.
Yeah. Let's see. We'll do that, and we'll do that. Oh. Now I'm upside down. Here we go. Interesting. All right. All right. So we have yeah, it's upside down Wednesday. it's a node, right, which has an integer piece, which we call data, and a next field, which in this case is a pointer to a struct node. All right. This is not recursive, it's not a problem, but if you use a type def, right, you can't define the type def until you've defined a struct node, so you can't use a type def inside here, but that's okay. Just call it a pointer to a struct node. Once we have done this, we can do things like this. Right, which would define n to be a variable that is a struct node, so it would be a variable that has these two fields. It's 16 bytes in memory, we saw that in GDB. This is usually not what we're going to do though, right? Almost always what we're going to want to do is define a pointer to a struct node. And this is going to let us modify where this points, which will be useful when we're manipulating data structures, basically. So the trick is, remember, if you declare a variable in C, it's not initialized for you. If I say integer I have no idea what the value of I is. Well, if I say struct node n is a struct node, but I have no idea what the value of it is. In other words, I wouldn't know what n.data or n.next were equal to. But if I say struct node star n, right, n is a pointer to a struct node, I have no idea what the value of that pointer is. So if I try to look at, the thing that n points to, I'll probably segfault. So usually after we do a struct node star n, we have to make n point somewhere reasonable. And the main way we do that is malloc. So we say malloc and we tell it how many bytes we want, and we don't put in magic numbers here. We say size of the type of thing that this is pointing to, which for us is a struct node. These two statements, if you're unsure, ask me questions, look at the notes, maybe talk about it in Discord. Stay far away from Stack Overflow and things like that, because there are a zillion ways to do this, and you know, all but a few of them will take you down twisty-turny passages that all look the same, and you may never come out of those, right? So this is a pointer to a struct node. This is allocating space for it using malloc. This is telling malloc how many bytes we want, which is enough for storing a struct node, because we said tell us the size of what a structure called node is. And I'm going to make a general general comment here that I alluded to yesterday. This sizeof operator, never ever 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 put the name of a variable in here. Okay? Always put in the type of a variable. Int, long, char star, struct node bracket 100, right? Something like that. Don't ever put a variable in here. If you do, I guarantee you will lose a few hours of productivity somewhere in the next several weeks. Sizeof is meant to tell you how many bytes a type of variable takes. So struct node is fine. N would not be fine. All right. Take that as you will. So this tells us how many bytes we need. It'll be 16. This will allocate at least 16 bytes of storage for us, and it will return the address where that block of memory begins, and this will set n equal to that. So from this point forward, I could say something like, take the thing that n points to, and let's set its data field equal to something. Or take the thing that n points to, and let's set its next field equal to something. All right, questions so far? So malloc just looks for free space, right? Yes. So malloc. Let's go to the source. So malloc looks for dynamic memory, right, in what's called the heap, and it returns a pointer to the allocated memory. It's suitably aligned for any built-in type, so we talked about data alignment yesterday, right? And if you run out of space, then it'll return null, or if something else goes wrong. The parentheses are not required. I'm just putting them in to clarify, right? First we want to find the thing that n points to, and then we want to grab the next field of that, or the data field of that. Without parentheses, the question is, am I talking about the thing pointed to by n dot data, or am I talking about the thing pointed to n by n, and then taking the data field of that? So I'm throwing in parentheses to eliminate any questions about how that would be interpreted, but we're going to completely get rid of those in a few minutes. So let's look at pointers. I always use parentheses personally. Someone asked, should we normally not use parentheses? I always use them. If I'm not absolutely convinced about order of precedence, I put parentheses in just so I don't have to think about it. Multiplication before addition, that one I pretty much believe deep down, so I'll leave parentheses off of that. But pretty much anything beyond that, and I just stumbled across a really, really quirky aspect of C that I never knew before about doing bitwise logic operations and comparison. And comparisons are actually done before bitwise ands and ors, which makes no sense, but it's apparently a leftover from the B language when B was turned into C a long time ago. and at that point there were no bitwise, there were no logical ands and ors, they were all bitwise. And so it's this kind of wart on the C language that you resolve with parentheses. So that kicked me back into using parentheses all the time. They don't hurt. If they clarify, go for it. All right, so let's just jump once more into GDB and look at pointers. So I have an integer I, which is a pointer to an integer. Let me throw in a few print statements here. Alright, so I'll have an integer pointer called I, and I will set the thing pointed to by I equal to 18. I didn't think I needed stdio, and then I ended up putting in printfs. Alright, so let's go inside our Go code, right? There's our code we're executing. So we'll start, we'll do our print. This is before we do the assignment. Okay, let's look at the value of I. I is 0, right? It just happened to be because I haven't given it a value yet. If I do this next statement, 7, which says take the thing pointed to by I and set it equal to 18, I'm asking the system to store an 18 at what address? Location 0, which is not an accessible memory location. So when I execute this next instruction, I get my seg fault. And it doesn't really matter what type of variable I'm pointing to. If I have a pointer to something and I try to use it before I've given it a value, I'll probably seg fault. Best case. Worst case, I'll store my value at some random location. So in this case, if I wanted enough space to store an integer, I could say call malloc sizeof, which will be 4, and that should set I equal to some reasonable value. I forgot to include standard lib, but that's okay. Alright, so before assignment, right, I is equal to 0. Once we call malloc, I has changed to a reasonable location. Okay, this is a spot that is accessible to my program, and if I look at that location, it's got a 0 stored in it right now. For no particular reason. There seem to be a bunch of zeros and a bunch of non-zeros in here. Alright, so I'm about to say star I equals 18, right? Remember, I is equal to this value. When I execute that statement, and then I look at this location in memory, it's got an 18, 12 hex. Right? So this sets I equal to crazy number, memory address. This says take the thing that I points to and set it equal to 18. I has not changed. I still has this value, right? But we changed the thing at the address pointed to by I. So it's an indirect reference. Engineering 270, think INDF, FSR 0. A thing to keep in mind, though, is I itself is stored somewhere in the system. Where is I stored? It's stored at this address, E3D8. And if I look at that location in memory, what do I find? I find the address that I is pointing to, this number up here. So there's always all this indirection that's going on. So let me write some of this down and give you a pointer. Get a better paper. All right, let's make a memory map. So at location, and I'll switch to my camera in a minute. So at location 7FFF, E3, D8, we find the value 5555. The value 18. Alright, so here's what we're talking about. The variable I is stored at this location in memory. At that location, we find this number. It's a 64-bit number, which is also a memory location. At that memory location, we find the number 18. Because we said the thing pointed to by I gets set equal to 18. All right, got the idea? This is largely review for most of you. All right, so let's talk about memory leaks while we're here. So in this program, I make this call to malloc. So use the replacement. Oh yeah. So make this call to malloc. Which says, give me some memory from the dynamic memory pool. Okay, variables like I that are set up by the compiler, when our program exits, right, those variables are released. They're mostly variables on the stack. When you see addresses, around the 7FF range, that's probably on your stack, right? So if you don't know what stacks are, you will in a few weeks. If you took 270, you know stacks very well. Stacks are storage areas that you can use for temporarily saving values, and they usually start at some location, and the address of the stack decreases, so it grows towards the beginning of memory. 7FFF followed by a bunch of F's is an address with 63 ones and a 0 in the beginning. It's the last address in the first half of all possible memory you can address. So it's 2 to the 63rd minus 1. And that's typically around where the stack pointer is initialized. So because, you don't usually have, 2 to the 63rd bytes of memory available in your system. So usually, the beginning of your address space has actual memory. And then there's a big gap, and then somewhere at the very end, we map more of our memory into. And so this is where local variables are stored, right? So I was a local variable that got stored in here. If I had, a character array that I declared, car bracket 100, that would be stored somewhere in here on the stack. And it's stored on the stack because when our program exits, or when a function returns, the stack area that was in use gets reclaimed. We move the stack pointer back. So it's a nice way to easily allocate and reclaim temporary storage. So local variables usually go on the stack. And in your main program, everything is local to main, even if it's a global variable. Because when main exits, all those variables should go away. But when we called malloc, we got this funny address up here, kind of like in the middle of memory. Okay, that's coming from a different set of storage, what's called the heap. And that is not going to go away when if we did that in a function and we return from the function, that value that we allocated is still in use, as it should be. Now, on Unix, when your main program exits, all of that space that you allocated is freed up. But on some systems, that's not the case. And if your program never exits, anything that you allocate is forever allocated unless you free it up. And so the flip side of malloc is free. It's a function we'll call when we're done with the space that we temporarily allocated. Okay, well, in my go-to.c, I do a malloc, but I don't ever free it. Right? I'm not worried about it because Unix will free it for me when I'm done, but it's bad practice to allocate memory and not free it. So there's a program we can use, which is valgrind. And valgrind will help us figure out where we have these kinds of memory leaks. So instead of just running, if I run my program, it works fine. But if I say valgrind and I run my program, oh man. Well, this works on the server. I forgot I'm not on the server. Okay, go to. Alright, so instead of just running your program, run it the same way you would normally run it, but say valgrind in front of it. And valgrind is kind of a envelope program that runs your program, but does it in kind of a sort of a sandboxy type area. So it can monitor what's being done with dynamic memory. When is it being allocated? When is it being freed? And when I run my program, right, it prints out my 2 messages before assignment, after assignment, and then it should exit. Okay, when valgrind sees that your program is exited, it will give you a report. And from this report, I can see I've got memory problems. So heap summary says, at exit, I had 4 bytes allocated in 1 block. 1 block probably means a single call to malloc somewhere. And the size of that block, 4 bytes. Okay, here's a summary of total heap usage. I made 2 allocations, I did 1 free. Okay, one of those allocations happened in the background, so did one of the frees. But this is where I have a problem. Right, I still have a block allocated. So if that happens, you'll get a leak summary. And it'll say you definitely lost 4 bytes in 1 block. Still reachable is when you have a reference to the allocated block that you could theoretically use to release it. Definitely lost means that you allocated memory, you saved the address of that in some variable, and then later on you threw that address away, typically because you allocated something else and stored the address in the same variable. Alright, you don't want these messages. Alright, PA2, you'll lose points for memory leaks. Very easy to fix in this case. When we're done, just call free with the same address that you got from malloc. So if I call free with an argument of I, that should release the memory that was allocated by this call to malloc, put it back in the dynamic memory pool. And now when I run valgrind, I get the happy message, all heaps were freed, no leaks are possible. That's what you want. So technically when your program exits with a leak, you've lost memory in the dynamic memory pool, which is, part of the operating system basically, right? And it's a combination of main memory and, offline storage that's stored on your hard drive. But Unix does free that for you, right? So I don't actually end up with a memory leak once the program exits. But this was a problem with certain browsers. At one point, there was a browser that if you ran it and you didn't close it out, your system got slower and slower over the next few days. And what was happening was there was code inside this browser that was allocating memory and then not freeing it completely when it was done. And so it was consuming more and more memory of the system. And people were saying, hey, I'm using this browser, my system's going really slowly, what's the problem? And the fix was just exit the browser and restart it. Because when you exit, the operating system will clean up all that storage for you. But if your program doesn't exit, it just keeps allocating memory, and you can actually, go into top or something, and you could watch your memory usage climb up and your free memory drop until there's so little memory that the operating system just can't run viably anymore. Alright, so we want to do mallocs to get storage, freeze to release them when we're done, valgrind to check to see if we've got any leaks. Alright, so let's go back to this business of dealing with pointers. So you use free as soon as you decide you're done with whatever memory you've allocated. And typically, that could be at the end of the program, but more often it would be in the middle. For example, suppose you're making a linked list program, and the user asks to delete a node, and so you go through, you find that node, you take the previous node, adjust it to point to the following node, and now you've got the deleted node. Well, it's still sitting in memory, so you would call free to release that. And that's the exact analogy to calling release node. Right, so exactly what someone said in chat. So if you never called release node in PA1, you could, add a node, delete a node, add a node, delete a node. After you did that 100 times, you'd be out of space. Right? Even though your list only had, 3 things in it, because you kept deleting nodes after you added them, but it would be chewing up that memory. So free is like calling release node. It's marking that block of memory as being available so that future calls to malloc could potentially access that. So get node equals malloc, release node equals free. Perfect. Security point here. When you call free to release a node, it goes back in the pool of available storage. Somebody else who calls malloc could get that same block of memory. If you have information in there that's security sensitive, it's possible you're exposing it to other users by freeing it. So some versions of free will zero out the contents of memory. You have the option of removing sensitive information yourself, but it's something to be aware of, right? Especially on a multi-user system. Now we have our own memory space when our process is running, but ultimately it's all one pool of main memory that's being shared by 100 some processes. So free doesn't actually necessarily delete or change values in the data, but it could. Right? So the other side of this is don't ever call free until you're absolutely done with that block. As soon as you free a node, you can't use any of the values in there. You can't assume those values are still intact. So we'll see that when we talk about delete functions. All right, so back to our struct node. So let's make a sentinel node. Now, if I'm declaring my sentinel node in my main program, right, I could make it a struct node, or I could make it a pointer to a struct node and then call malloc. I'm just going to make it a struct node here. And if I need its address, I can use an ampersand. But this is not only saying sentinel is a variable of this type, but it's allocating space for it. Right? So this is actually going to, when I run my program, set aside a chunk of 16 bytes somewhere and set sentinel to be the address at the beginning of that chunk. And my initialization program will do what? It'll basically set the next field equal to null and maybe set the data value to something something recognizable, so that if I stumble across my sentinel's data, I'll recognize it. So we could initialize like this. Now your init function will look different in PA2 from PA1, but most of your other functions are going to look the same. Alright, so what's this going to do? It's going to basically set the next field to null. So that's our empty list. So let's suppose we have a list like this, and we want to move down the list, right? So we always have to do this when we're adding or deleting or printing. So how would we print the contents of this linked list? Same thing that we did in PA1. So I'm going to have a temporary variable which I'm going to call current, and it's going to be a struct node pointer. Instead of an integer index into an array, it's going to be the memory address of a node. That's what a pointer is. So I would probably initialize it to the thing that sentinel points to. So if sentinel is actually this node, right, because I did something like this, right, if I actually declared it to be a struct node, then I can set current equal to sentinel.next. This is going to be my current. But I'm potentially getting confused now, right? Because sentinel is a struct node, and current is a pointer to a struct node. And that's just kind of begging for confusion. So let's do this a little differently. Let's make sentinel a pointer to a struct node. And this is going to let me do the following. It's going to let me set Sentinel equal to the return value from an initialization function. And what init is going to do is allocate some space for a struct node, set the next field equal to null, and return the address of that node. And so this is what I said yesterday, we're almost always going to deal with pointers to struct nodes. The reason being, in this case, because when we build up a linked list, each of these next fields is going to be a pointer to a struct node. So we'll have a pointer here, we'll have a pointer here, we'll have a pointer here, and so on. So if Sentinel is a pointer to a struct node, then this becomes the thing pointed to by Sentinel. Take the next field. So now current is the address of this block. To print out the data field, what do we print? Take the thing pointed to by current. Grab the data piece of that structure and print that out. And then how do we move down the list? Take the thing current points to, grab the next field, set current equal to that. And that's going to make current look like this. And then go back up here. And we're going to do this loop until we get to this last node. So at this last node, right, we'll print out the data field right here. We'll set current equal to current, the thing current points to's next field, which will be this. So at the last node, after we've printed its data, current will be equal to null. And so we can put this all in a while loop while current is not equal to null. All right, questions so far? Null is a pointer to 0. I think we can probably find it. But we can probably find too many of them. Yeah, I don't think we're going to find it in here. I think it's defined further down. But if you go through, because these include files, include other things as well. But if you go through all of this, eventually you'll find null. And null is, its value is 0, but it's actually declared to be an object of type pointer. And it points to 0. Yeah, go through here and try to find it. It's a fun exercise. Okay, maybe not terribly fun, but you know, a little fun. So it's a 0, but don't ever code a 0, right? Chances are, I won't do this to you, but other teachers, if they see you comparing a pointer to 0, you'll probably get a 0 on the assignment, because that's just like a grave invitation to problems down the road. So always use NULL uppercase when you want to see if a value, you know, that was returned by malloc is saying out of memory, or if you're looking for the end of a linked list. So at the end of a string, we find what's called the null terminator, but the null terminator is actually just an 8-bit value, and it's the character with ASCII code 0, which we can represent like this. But that's just an 8-bit value. It's a short int. Whereas null is, you know, on a 64-bit system, it's a 64-bit value. It's an 8-byte entity that's equal to 0. On a 32-bit system, it's 4 bytes, but it's a pointer, right? So you use it in fundamentally different places where you use the null terminator on strings, which is just a 8-bit character. Confusing terminology. All right. I got weird software issues. All right. Syntax issue here. All right. If you miss this, everything will get confusing. We're going to write things like this and this and this a lot, right? Because we're almost always going to deal with pointers to structures. When we want to access the field of a structure, inevitably we end up writing the thing pointed to by this pointer dot the name of the field. Okay, there's a shorthand we can use in C for this. So in this case, instead of star sentinel dot next, we can do the following: sentinel, and then an arrow, a minus sign followed by a greater than sign, and then the name of the field. Instead of star current dot data, we can say current arrow data. Instead of star current dot next, we can say current arrow next. And you always want to use this kind of shorthand. Don't write things like that unless it's when you're first writing this and you're trying to understand exactly what's going on. Go ahead and do that. But once you understand it, switch to the arrow notation. And the way that I read this in my brain, like deep down, is the arrow tells me take sentinel, see what it points to, and then grab the next field. Take current, see what it points to, and then grab the data field, and so on. And there's a reason for that shortcut. So suppose we have our linked list here and we wanted to access this node right here. So let's say we wanted to look ahead, right? Well, I could do this the old way by saying take the thing that sentinel points to, that's this box, grab its next field, that's this box, take the thing that points to, that's this node here, take its next field, that's this box down here, take the thing that points to, which is current, and then pick up the data piece of that. That would get me to my 20. Alright, unless you're a fan of Lisp, you don't want to write code like this. With this arrow notation, this looks like the following. Sentinel next data. And here I don't use parentheses because I believe in my heart that this will do the right thing. And it almost always does. So this says take Sentinel, look at the thing it points to, take the next field, look at the thing it points to, take the next field. Oh, I did one too many. I'm actually getting to the 30. Start with Sentinel, take the next field, which is this, take the next field of that. No, that's right. And then take the data field. It is a strong belief. All right, so this reads a whole lot more naturally than this for most people, right? Sentinel next gets us here, next again gets us here, data gets us to the 20 field. Now we don't usually do this, but sometimes we have to. And linked lists are our simplest data structure. We're going to move from here eventually to binary trees, and in binary trees, it's not unusual to want to look at, you know, one node, the thing it points to, look at the thing that points to, and look at the thing that points to. When we do what's called balancing, red-black trees, for example, we'll end up doing things like this all the time. And eventually your brain will see this as, oh, go to next, go to next, go to 20. So you get to practice with this while we're developing code for linked lists. All right, so that's some of the mechanics. What we'll do tomorrow is we will start looking in earnest at doing the things we did in PA1 with linked lists. So initializing, printing, searching, adding, deleting, using this kind of structure. And then we'll talk about PA2, which is basically PA1 using dynamic memory instead of a fixed array. And then you're all set. All right, I will see you next time. Have a good one. Thanks.